Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to finite element methods. In the last class, we have seen the application of method of least squares to one-dimensional problem. In the present class, let's use the same method of least squares to a 2D problem. Let us choose the same two-dimensional beam, whatever we have solved before earlier. In the present case also, let us solve the same beam using method of least squares. Okay. So what is the setup of the beam? So here this is a two-dimensional beam where the top and the bottom are fixed and the left and the right are having simply supported conditions. So this is simply supported condition and this is fixed condition. So what are the boundary conditions? Let us revise once more. Boundary conditions. So what are the simply supported boundary conditions? If you assume this as x and this as y, this dimension as x, this dimension as y, and the plane perpendicular to the paper is z, the dimension that is perpendicular to the paper is the z direction, then with this setup, so what are the boundary conditions for the simply supported, that is for left as well as on the right? What are the boundary conditions? So one thing is w at 0 comma y is equal to w at b comma y equal to 0. Fine. In a similar way, since that is simply supported, the moment is 0 at those positions. So if the moment is 0, it is nothing but the curvature is 0 at those positions, right? So that is dou square w by dou x square at 0 comma y equal to dou square w by dou x square at b comma y equal to 0. Okay. So these are the simply supported boundary conditions. And what are the fixed boundary conditions? W at x comma 0 equal to 0 and w at x comma b equal to 0. By the way, I am writing b here. B is nothing but, let the dimension of the beam be b by b. I mentioned this one in the earlier class. So here w at x comma 0 is 0 and w at x comma b is 0. Similarly, since these are the fixed boundary conditions, the slope is also 0 at those positions. That is dou w by dou y equal to 0 at y equal to 0 and y equal to b. Is it clear? So these are the boundary conditions for the simply supported and these are the boundary conditions for the fixed condition. Okay. By the way, what is the governing equation? The governing equation for a 2D beam is del power 4w minus q by d equal to 0, and I have defined each and every term in the last class and I have derived what is this del power 4 in 2D, that is the biharmonic operator, that also I have derived in the last class. So what does this w indicate? W indicate the deflection in z direction or the direction perpendicular to the plane of paper. Similarly, q indicates intensity of loading and d indicates material parameter, especially for beam. D represents flexural rigidity, that is D is nothing but EI. The product of Young's modulus and the moment of inertia is called flexural rigidity, and this D is nothing but EI in the case of beam. Okay, so now we are having our governing equation. And we are having our boundary conditions. So now how to solve this using method of least squares? The same way. So first what we have to do, we have to assume some solution, right? Let us take the same solution that we took in the previous class. So let us assume let the trial solution be W tilde of x comma y is equal to a1 sin pi x by b into 1 minus cos 2 pi y by b, and we have checked that whether this assumed solution or the trial solution is satisfying the boundary conditions or not in the last class. It's very easy, just keep x is equal to 0 and x is equal to b, it will be satisfied. Since this is a sine term and the double derivative of this sine term will again be the same sine term, so the condition of the simply supported will be satisfied by this term, and the condition of the fixed boundary conditions will be satisfied by this proper term. Okay, so the product will be a solution for our problem. Okay, so with this solution, now I have to calculate the error term or the residual error, comma, capital E is nothing but, so how do we define error? Since this is a trial solution, this won't satisfy our governing equation completely. Some quantity, something will be left over. That leftover is nothing but our residue, so, or error. So how to calculate this residue? We have to substitute our trial solution in our governing equation. Okay, so just substitute this one in our governing equation. That is del power 4 W tilde minus q by d is not equal to 0. That is nothing but our error. So upon substituting, we simplified this one in the last class. You can refer that in the previous lecture. So I'm not going to do it again. I'm going to write the error term directly. So the error term is nothing but pi by b whole power 4 a1 sin pi x by b into 1 minus 25 cos 2 pi y by b. This is our error term. Okay, so now by method of least squares, we are going to make this error to 0 in an integral sense, isn't it? So how are we going to make it in an integral sense? Integral error multiplied by the differentiation of the error with respect to the parameter over the domain and make it to 0. Okay, good. So here our domain is a 2D domain. So obviously here not the single integral, we will get double integral, and our domain varies from 0 to b, 0 to b, these are the limits, and this is the error term. And how many constants we are having here? We are having only one constant, that is dou capital E by dou a1. So what is this d omega? This is dx dy equal to 0. Okay, so we are having our error term in our hand. Just substitute that error term here, differentiate the same error term with respect to the constant and substitute that parameter here and simplify this one to get the constant a1. Okay, so I am rewriting the error term. Our error term is capital E is nothing but pi by b whole power 4 a1 sin pi x by b into 1 minus cos 2 pi y by b. So if you differentiate this with respect to the constant a1, this is nothing but pi by b whole power 4 sine pi x by b, here 25 is there, into 1 minus 25 cos 2 pi y by b. So just multiply these two terms, integral 0 to b, integral 0 to b, a1 sine pi x by b into 1 minus cos, 1 minus 25 into cos 2 pi y by b into, now the differentiation of the other term with respect to a1, that is nothing but into sine pi x by b into 1 minus 25 cos 2 pi y by b. Agreed? Did I forgot anything? I forgot that pi by b whole power 4. Yes. Okay. Into dx dy equal to 0. Solve this integral for a1. It's a very direct integral. Just you are having the product terms. Just calculate that sine cosine terms using trigonometry. Then you can calculate this easily. Then find out the constant a1. Then that turn out to be, you will get a1 is equal to q b power 4 by d into 0.415 into 10 power minus 4, and the approximate solution is w tilde at b by 2 b by 2, that is at the center of the beam, at the center of the 2D plate, okay, is given as, the approximate solution is 0.00083 q by d. If you solve this integral, you will get a1. Since you got a1, then our w tilde is completely known now. Then substitute x is equal to b by 2 and y is equal to b by 2 in our approximate solution. Then you will get the deflection at that particular point. That it will turn out to be 0.00083 q by d. But what is our analytical solution? We know the analytical solution, right? So if you compare this one with the analytical solution, this is pretty far away from the analytical solution. So this is not a good solution. Note, not a good solution, right? So I have written the analytical expression for this in the last class. So the analytical deflection is 0.00195 q by d. It has to be L power 4 will come here. So this is our analytical solution. This is our approximate solution from method of least squares. This is from method of least squares, which is far away from the analytical solution. So that is why this is not a good solution. Okay. Now in the next class, we will see another weighted residual form. By the way, this is one of the weighted residual form. This method of least squares is one of the weighted residual form. And in the next class, we will see the most famous weighted residual form, Galerkin method, and we will see the magic of that method. That is, it will give you very good solution when compared to all these things. We will see how it will give the better solution. So what are the changes we will make from the method of least squares to the Galerkin in the next class. Thank you so much for watching this video. Stay tuned to Ekeeda. Subscribe to Ekeeda.